Welcome all of you. In the last class, in fact last one or two classes, we discussed lot about spin echoes and polarization transfer techniques. In the polarization transfer technique, I told you about possible ways. One is selective population saturation, selective saturation, or selective population inversion. Both are possible. I showed that taking example both in the homonuclear case and in the heteronuclear case. Two coupled spin system we took. And when I took example of proton with carbon, I showed that when I saturate one of the proton signals, one of the proton peaks, one of the transition corresponding to proton, then the carbon 13 two transitions enhance in the signal intensity. Of course, with the, they were out of phase, antiphase, -5 and +5 intensities. Okay, and we also understood after this thing how we can do the polarization transfer. We can apply it by bringing in another factor called what is called spin echo. In this sense, we put a 180 pulse at the center of this INEPT sequence, and we wanted to ensure that chemical shift is also refocused. At the same time, transfer is also going to take place. There is the enhancement of the signal intensity. So this is one of the biggest advantages of INEPT. I told you, always INEPT takes place only between the coupled spins, and the magnetization transfer takes place from anti-coherence to anti-coherence. So we created the anti-coherence for the proton after applying a 190 pulse. When after exactly 1 hour 2J, it became antiphase, and then we apply simultaneously 90 pulse on both proton and carbon. The coherence from proton jumped into carbon 13. That's what we observed, and we calculated the intensity, and we know that how it works out everything diagrammatically, and by a vector diagram we try to understand everything. Fine. And afterwards, when we understood, there is because we need to do the decoupling of this thing, we also wanted to give a delay after this thing so that the antiphase become in phase in character. So -3 and +5 should become +3 and +5, so that we can do the decoupling. This also we discussed. But however, there were 2 points which we need to be addressed. One is suppression of the natural abundance signal and converting antiphase to in phase for decoupling. In fact, we did this, we understood this, how to do this when we were trying to understand the spin echo, this decoupling. We can adapt that here. 2 points we have to address: suppression of natural abundance and converting antiphase to this thing, in phase signal. Both these can be addressed individually. There is no issue at all. For suppression of the natural abundance carbon 13 signal, we have to carry out 2 experiments. One proton pulse, the detection pulse we apply, 90-degree pulse for coherence transfer from proton to carbon. That once you have to do 2 experiments. The last proton pulse, one should be +5, 90 +5, other is 90 -5. 2 experiments you have to do. And what happens when you do this 2 experiments, we will see how it works. We saw the pulse sequence, how it is working, everything here. Already we discussed quite a bit. Up to this we have discussed. At this point, what is going to happen, we will see at that point. Okay. At that point, F, just before applying a 90-degree pulse, 90 pulse, the proton signal, 2 vectors are antiphase to each other. Alpha and beta components are antiphase to each other. All right. Just after 90 pulse, I told you they were in the antiphase to each other in the y-axis, and applying a 90-degree pulse takes them back to z-axis. One alpha component goes to +z and beta component comes to -z. That we saw. And then at F, what happens to carbon 13 signal? This is as far as the proton is concerned. Just before 90-degree pulse, one is +5, other is -3. That is the carbon signal. We saw that. Signal intensity for C alpha is +5, C beta is -3. Okay. Just immediately after the 90 pulse, what happens to carbon 13 signal? And then again, what will happen is, but till now, when we are looking at the proton, the coherence was in the xy along the y-axis or x-axis, whatever the axis you have chosen. Whereas we have carbon 13 still was in the z-axis. Now what is going to happen? After applying a 90-degree pulse, you brought the spin vectors of carbon 13 into y-axis. Now again they are antiphase, because coherence has transfer has taken place from proton to carbon, and C beta is minus 3, C alpha is plus 5. From Z axis and minus Z axis, you brought it to minus 5 and plus 5. Minus 3 and plus 5 is the component. All right. This is one experiment with 90 plus y. What happens if you do the identical experiment with proton pulse 90 minus y? So, what is happening is, this is 90 plus y, of course as usual at the point F, just before application of 90 pulse, we have the signal like this. That is exactly similar to before. Now, we are applying a 90 pulse minus y. When you apply 90 minus y, remember in the previous case H alpha was along Z axis, H beta was along minus Z axis. Now, they get reversed. H beta is along Z axis, H alpha has come to the minus Z axis. That is what happened. So, this magnetization got inverted because we are applying a minus y pulse. Further, what is going to happen for the carbon 13 just before 90 pulse, it was like this, because we have not touched it yet, So, now what we are going to do is, because of this it is happening like this. As soon as I apply 90 for the carbon 13, what is happening is the C alpha which was along plus y came to minus y, and C beta which was along minus y came to plus y. This is what happens. See, when you apply 90 pulse, I do the two experiment, once with plus y and once with minus y 90 pulse. This is what is going to happen. When you apply simultaneous 90 pulses, we are changing the magnetization from C beta C alpha in two experiments. Once it is along C alpha is along plus y, and other time it is minus y. Similarly, C beta also once in minus y, second time it will be on plus y. Now, with plus y 90 pulse, this is the magnetization of carbon 13, and with minus y, this is what it is. Now, in both the experiments, the natural abundance carbon 13 is detected with constant phase, that we are not touching. We are only transferring magnetization to this thing from proton to carbon 13 for one of them. Natural abundance carbon 13 still continues with the constant phase. The first FID and the second FID, we are going to do the experiment recorded with two phases of 0 degree and 180 degree for the receiver. That is what we have to do. What we have to do after doing this experiment, subtract experiment 1 with experiment 2. Okay, 90 degree Y pulse experiment 1 with experiment 2, we will subtract. See what is going to happen. This is 90 degree Y pulse, subtract this with this one. What is that you are going to get when you subtract this one? And net intensity of each of them, you calculate here minus 3 and minus of plus 5. So, this is going to be minus 8 C. Similarly, the other one plus 8 minus of minus 3, which is going to be 8. So, minus 8 and plus 8 is the intensity. The two transitions have intensity minus 8 and plus 8, gone up 8 times. Okay. So, that is okay. I mean, it was 2, okay, 4 times at it is gone up. The natural abundance carbon 13 will give a constant phase signal in both the experiment. This is a transferred magnetization. Carbon 13 natural abundance is not transferred, it remains same. The elimination of natural abundant carbon 13 signal, you have to change the receiver phase by 180 degree to eliminate it. How do we do that? First, we do one experiment 90Y with 90Y pulse. We have signal intensity 5 and minus 3 for magnetization, which correspond to H alpha, carbon magnetization, carbon vector corresponding to H alpha orientation, and carbon vector corresponding to H beta orientation. They have plus 5 and minus 3 orientations with one pulse plus 90Y pulse. And what we are going to do is, with a natural, this is equal to what we observed is equal to natural abundance magnetization, which is natural magnetization of carbon 13, which is not transferred. So, it is intensity 1 because it is a doublet, we will 0.5 0.5, we will take 1 and then transferred magnetization is of course antiphase minus 4 and plus 4. Why did I take minus 4? Because gamma is 4 times smaller. So, we know it has to be 4 times gain. So, I have written transferred magnetization has to be minus 4 and plus 4 antiphase. Natural magnetization is identical 1. This is with 90 pulse. Do another one with the 90 minus y pulse. Then what is going to happen? This is natural magnetization, but here this gets reversed now, because we are applying 90 minus y pulse here. Natural magnetization will of the carbon 13 will continue to be in the similar phase, constant phase. That phase won't get disturbed. Whereas these two signals will the phases get reversed. Once this is negative, this is positive. Second time this is positive and this is negative. Now we already got the idea. What we can do? We take the difference of the two experiment. When you take the difference of the two experiment, what is going to happen? The signal coming from the natural abundance carbon 13 gets cancelled out because they are of the constant phase. Only the transferred magnetization is retained. This is what happens. Because when you take the difference of here, this and this gets nullified, cancel out. Whereas this will get added up. When you take the difference, minus of this one, minus of minus plus 4, this is minus 8 and this is going to be plus 8. This is what we are going to see. Minus 8 and plus 8. Here the advantage is we have eliminated the natural abundance signal from the carbon 13 and we have retained only transferred magnetization from proton to carbon 13. Okay, now some interesting things do happen here. The signal intensities, what will happen to signal intensities for CH2, CH3 etc. in INEPT experiment? So far we are dealing with only CH carbon and carbon 13 when it is coupled to single proton will be a doublet. So we were dealing with only doublet, we got minus 3 plus 3, minus 3 plus 5, all signal intensities, antiphase. We knew how to convert this into the, give a delay and afterwards it is going to become converted to in phase. We can do the decoupling, everything we understood. For CH2 groups, what is going to happen? The signal intensity will be like this. One dimensional carbon 13 signal will be in the ratio of 1:2:1. That's correct. There is no difference. As soon as you put the INEPT experiment, in the INEPT experiment what happens? Central peak do not precess and there is no transfer of magnetization for that. That will not precess at all. That won't get transferred. No magnetization get transferred. Only for components, outer components which are in antiphase, there is a signal. Okay, that's where, as I told you, the transfer of magnetization takes from antiphase to antiphase. Only these two will get the signal. And how much is the gain in the signal? You can find out from this. This is the gain in the signal intensity. Okay, so if you put that value, the intensity of the CH2 peak are minus 8, 0 and plus 8. Central peak will not get any magnetization transfer, whereas outer components will have minus 8 and plus 8 intensity. This is what happened for a CH2 carbon. What about the CH3 carbon? CH3 carbon intensity is 1331 in a normal carbon 13 spectrum coupled to 3 protons. That we know. Intensity is 1331. Now what we will do is in the INEPT experiment, it is analogous to CH carbon where it is attached to a single proton. Instead of doublet, now we have a quartet with 2 lines, 1331 ratio. 2 precessing in the two orientation, one clockwise and the anti-clockwise. Fast moving and slow moving will be there. 2 will be fast moving, 2 will be slow moving. Again they are antiphase like this. And if you calculate the intensity ratio for INEPT experiment, it turns out to be like this. For the carbon 13, 4 peaks. And if you look at the intensity, this is minus 12, 12, 12, 12. Very easy. Okay. This is the intensity. You are going to get minus 12, plus 12 and plus 12. These two are minus 12, minus 12. These two are plus 12, plus 12. So it is very easily you can understand for this one. The signal gain should be 4 times. When there are 2 carbons, it became 8 times. When there are 3 carbons, it is 12. That's all. So gain is, this is very easily, it depends upon the number of protons attached to carbons. That's how CH3 group will come. Now the coupled INEPT, an experiment, if you see, it looks like this. Coupled INEPT experiment, an example of a molecule called coumarin. This is a molecule. We have only CHS here, no CH2 or anything, only no, but of course there are quaternary carbons here also. When you do coupled INEPT, that means we are not removing the coupling. That means after the INEPT there is no delay is given. Okay, no delay is given and we are not going to acquire the signal with decoupling. And of course, in which case if you do the INEPT, the coupled INEPT, this is what it is, because they will be antiphase in character. we don't need to worry about decoupling, means antiphase is still okay, because there is no question of getting signal nullified. Only when you want to decouple, then this will get nullified. All the opposite negative into positive negative gets cancelled out. But that is not going to happen, because we are looking at the coupled inept. Same thing if you do the gated decoupling, where it is coupled but still get the gain in the intensity because of the gated decoupling. Look at this one. This is what the comparison intensity ratio. There is small gain in the intensity. But if you look at this thing, there is small gain in the intensity. Of course, if you look at the signal to noise ratio, you have to see. Okay. And then with this, all right. So far we have not done the decoupling. We have been doing only, what we did is suppress the natural abundance carbon 13 signal. We can do what is called a refocused inept. The same inept experiment with a 180 pulse which in the middle as a spin core for refocusing chemical shifts. We can extend further. This is the refocused inept. The refocused inept will circumvent the problem of decoupling due to antiphase character. This is what one of our this thing, which we already discussed in the spin core when we discussed. There is nothing new in this. All we have to do is we have to give a delay after the last pulse, which is equal to 1 over j, 1 over 2 j. But then you are going to see what is going to happen here. Up to this is known. This is up to f is regular inept. For the refocused inept, we are going to give like a spin core sequence. There are 2 delays in between with 180 pulses on both proton and carbon. What is going to happen for this now? Let us see what is going to happen, especially for this part. Up to this we know, we have already understood. At the end of the first delay, especially here, then the doublet component of CH spin system would have acquired a relative phase difference. Okay, that is true. They would have acquired some relative phase difference. 180 pulse on the X nuclear refocuses the chemical shift. 180 pulse on proton inverts the alpha and beta spin states of X vectors. It will invert it because it is coupled to that. So, it is a doublet. If we, as I told you already, applying 180 pulse will invert alpha and beta labels. Labels get interchanged. That is what is going to happen. Now, what is going to happen? The magnetization corresponding to C alpha, which is coming because of the H alpha, becomes now M magnetization corresponding to H beta. Magnetization of carbon coming because of H beta now becomes magnetization vector coming because of H alpha. This is what the 180 pulse has done. It just inverted the spin states. That is all it is done. Okay. This is what I said. It inverts the alpha and beta labels. That is what it did. During the last delay, what will happen? In the last delay, that delay 2 180 pulses and delay is the last delay. The last delay, 2 carbon 13 vector continue to precess clockwise and anti-clockwise as always. There is a delay you give and then they continue to precess. One is fast moving, other is slow moving. One goes clockwise, other goes anti-clockwise. And after certain delay, they again come back to the x-axis. This is what you understood in spin echo. When you understood, it gets refocused again with this delay. And this is what we have to understand how it happens. At the end, at the F, the regular inept, at the end of the regular inept, we understood carbon 13 vectors are antiphase, -3 and +5. That we know. After the first delay, they started evolving like this. Fast and slow moving components are moved by some angle for some delay. You apply a 180 pulse now. What is going to happen? The labels get interchanged. H alpha and H beta label gets interchanged. And after second delay, what is going to happen? They will move and then come back and then get refocused along the plus x axis after another delay. So, again it is delay, everything is given. First of course 180 pulse is to invert the alpha and beta spin states. And then second delay will ensure these vectors continues to move after getting inverted and then get refocused along the x axis. This is what is going to happen after F. Alright. Now we can do the decoupling of proton with carbon 13. Why? Because you can see both are in phase vector. If it is in phase vector, decoupling is possible. Only if it is antiphase vector, there is an issue. Then signal gets nullified. Okay, we can do the decoupling. You may ask me a question. We said there is a delay, but what is the refocusing delay we have to use? Of course, we have already discussed this when we were trying to do the spin echo with decoupling. Even a simple inept experiment we saw, and we saw that when the signal is antiphase, what is going to happen if you don't give the delay, it gets nullified. We saw that. And then how did we overcome this issue? By giving an extra delay. That exactly. We also know how much delay we have to give everything, but we will again understanding. What is the length of the refocusing delay? That depends upon, you have to choose the optimum value. That depends upon the J coupling between carbon and proton, 1 bar. We are not worried about long range couplings. Length, this period has to be calculated based on 1 bond coupling. Okay. And the delay of 1/2J gives the maximum refocusing. Maximum signal only for system like IX, where like 2 protons are coupled, like two heteronuclear are coupled like carbon and proton. In such a situation, if you consider CH, if you put delta is equal to 1/2J, you get maximum refocusing. That's what is going to happen. If you put the delay equal to 1/2J, there is a refocusing for this type of things. For CH2, when do you get the maximum refocusing? See, CH, J coupling is between these two. It is, two vectors. If in fact it is half J. One is this side, one is this side, and your on resonance is at the center. For CH2, central peak is here, and other two peaks are equal to J, moved apart. For fast moving, slow moving component already not half J is 1J. For CH2 systems, the refocusing is maximum when delta is equal to 1/4J. The delay has to be 1/4J. And if all the multiplicities are there, CH2, CH3, etc., and all these the different carbons attached to different protons will have different J couplings, and you cannot keep on varying the delay and according to J for different CH, CH2, CH3 carbons. What we have to do is we have to arrive at the compromising setting of the value. Delta approximately equal to 1/3J is an appropriate value, more or less is approximate. It is there is no preferred value, but approximately 1J CH is 150 Hertz is taken, and 1/3 of that days is given as the delay. That is appropriate for all the multiplicities of CH, CH2 and CH3 being refocused. So the refocus INEPT, now you can use this to edit what is called the spectrum based on the multiplicity of the carbons. How? We already discussed. CH carbons, if you put delta is equal to 1/4J, all the carbons CH, CH2, CH3 carbon appear as positive signals. Exactly at 1/4J, all carbons are positive signal. At 1/2J, if you give, only CH signals are seen, others are not seen. If delta equal to 3/4 of J, interesting thing is CH and CH3 signals are positive and CH2 is negative. Very interesting is going to happen. At 1/4J, all are positive, 1/2J, only CH signal is seen, and at delta equal to 3/4 of J, we get positive signal for CH and CH3 and negative signal for CH2. So now what you are going to do, based on this phases of the signal, you can identify different carbons. Compared to, in fact, APT we did that. We saw that in the APT when exactly equal to 1/J, 1/2J, we found that all signal CH, CH2, CH3 will be 0, and then only quaternary carbons will be seen. And at 1/J, we found that only 2 of them are positive and other is negative. We saw that CH2 is negative, CH and CH3 were positive. But between CH and CH3, we were unable to distinguish which and which. But here we can utilize this to find out very easily. See, these are the things now. Signal intensity, I have made a table here of different carbons during refocused INEPT. Put a delta value is equal to 1/4J, CH is positive, CH2 is positive, CH3 is positive. Put delta is equal to 1/2J instead of 1/4, you will see only CH carbon, other two will be disappearing. Put 3/4 of J, this is positive, this is positive, this is negative. This is the intensity pattern, phases of different signal depending upon the delay delta. All right, this is what you will see. Variation of the 13th signal intensity in the refocused INEPT as a function of delta. This has been plotted as a function of delay time. It is I have chosen only 3 for the different values, but here continuously the value was varied delta, and intensity for different carbons were plotted. Look at it at exactly 1/4J, all are positive. At 2 or 1/2J, then what is going to happen? This CH carbon is, and CH3 carbon and CH3 carbon both are 0. It is going to 0, exactly at 0. Whereas CH carbon is positive for 1/2J. Go to 3/4 of J. Now CH2 is negative, both CH and CH3 are positive. So using this, you can identify different carbons. You can also get a decoupled spectrum. You can do the decoupling by using this refocused INEPT. At the same time, by manipulating the delay, you will be able to identify different carbons attached to different number of protons. This is what it is. You can compare the intensity, how beautifully INEPT works is being compared in a simple example for a molecule like this. This is called chloroform. In the chloroform, we have only 2 spin-off nuclei, heteronuclei, carbon 13 and proton. So if you look at carbon 13, obviously it is going to be doublet because of its coupling with proton. I will take a normal carbon 13 spectrum, no decoupling, no NOE, nothing. NOE I am going to discuss after another 1 or 2 classes. Remember, I told you earlier, NOE gives you signal enhancement of the signal intensity, one way of transfer of magnetization like INEPT. Here you use J coupling, there no J coupling, it is only spatial proximity. That is what I said. We will discuss more about it later. If you take a normal carbon 13 spectrum of CaCl3, no NOE, no decoupling, you get a doublet like this of this intensity. Same thing you do INEPT experiment, not refocused INEPT, just INEPT experiment, in which we saw there is opposite phase. We get doublet, one is positive intensity, other is negative intensity. We do not do the decoupling. If you do decoupling, it gets nullified. It is a coupled spectrum, no decoupling. Same thing you do refocused INEPT. What does refocused INEPT does? It will convert this antiphase into in phase. That is all. That is what happened. Again, no decoupling. As a consequence, you still get a doublet. That is also fine. What we have to see is this is the refocused INEPT. What is the refocused INEPT? This we are going to make antiphases in phase, plus we do the decoupling. Collapse this multiplicity doublet into a singlet, and we are going to get a single peak like this. And this is a normal spectra with decoupling and NOE. Here without decoupling, without NOE. Here with decoupling and NOE. Look at it. There are different types of experiment has been done here to make a comparison. Look where do you see the better signal? We want to identify decoupled spectrum attached to different carbons attached to different protons. At the same time, there must be gain in the signal intensity. Obviously, you will see the refocused INEPT with the decoupling gives you a better spectrum. The intensity is positive and much better compared to conventional experiments. This is a conventional experiment with decoupling and NOE. Here no NOE at all. And this is what we have advantage. There is a gain in the signal intensity here because of, I am sorry. And this is the this is the signal intensity which is coming because of INEPT, refocused INEPT. And now we will compare this with the sensitivity of the INEPT with the direct detection of low gamma nuclei. Some low gamma nuclei, nitrogen 15. Nitrogen 15 spectra of Gram-17S acquired with refocused INEPT. Refocused INEPT. This is a INEPT experiment. The normal nitrogen 15 no NOE. This is a INEPT experiment where you see the enhancement of the signal intensity. with decoupling. Fantastic experiment. So beautiful. We can see the nitrogen 15. Of course, INEPT experiment can be done to any other nuclei. Need not be carbon 13 or nitrogen 15. INEPT enhancement of on the rhodium 103, where the polarization is transferred from phosphorus in a molecule like this. Here there is no decoupling has been done because of its antiphase character. That is why you look at the antiphase. But here is the normal spectrum. See, this is signal. So weak, you will not be able to see anything. This is a simple inept antiphase character without any, it is not a refocused inept. See, already a gain in the intensity. In case if you do refocused inept with decoupling, you get a better signal. See the advantage of inept. This is called a polarization transfer experiment, where you take the magnetization from the abundant spin and giving to rare spin. In the previous example, we took from proton and give it to carbon and nitrogen. Here, phosphorus is abundant. Take the signal from phosphorus and give it to rhodium. This is what we do. And of course, you can compare the intensity of our different nuclei. We can do the comparison. And if you do the comparison, how much is the gain during polarization transfer and what is the maximum intensity gain you will get with NOE. They can be easily compared. Polarization transfer from proton to heteronuclei like this. For example, in the case of rhodium, 30 times enhancement of the signal you get. For iron, 30. For example, carbon 4 times, silicon 5 times, nitrogen 10 times approximately. And this is the advantage of this. So, of course, depth is another called distortion enhancement polarization transfer. I already discussed this. This is one which uses to distinguish different carbons attached to different number of protons. This uses polarization transfer I told you when I explained carbon 13. But I did not explain polarization at that time. Now with the understanding of polarization transfer, you know what is depth. So simply I will show you an example of the depth sequence. This is what we discussed. And then intensity of the different carbons as a function of flip angle, especially the last flip angle here on the proton. And if you consider, see how the signal is changing. At 45 degree, all the signal are positive, CH, CH2 and CH3. At when it is 90 degree flip angle, CH2 and CH3 are 0. And 135 degree, what is going to happen? CH3 is positive, CH is positive, CH2 is negative. This is how we can do the and I identify different carbons attached to different protons using depth. This will I already discussed this during carbon 13. I just told you the advantage of polarization transfer. So compared to APT, the advantage of depth is you can still identify different carbons attached to protons, but there is a gain in the intensity because of polarization transfer coming to that. So this is the advantage of depth versus APT. Both the experiments are used to identify different carbons based on the multiplicities. Depth requires less experimental time because it requires only because of polarization transfer, but accurate phase of the decoupler channel is needed. APT is easy to set up, requires calibration with a perfect 90 degree pulse, and no need to wait for carbon 13 T1 to repeat experiment. But one disadvantage is depth is it cannot distinguish between CH and CH3, whereas in the depth experiment I showed you we could do that. So this is what it is. So I just wanted to summarize this, and with this polarization transfer experiments have been completely covered. So in this what we discussed is, we discussed about the refocused inept. At the same time, how do you separate the natural abundance carbon 13? We saw the gain in the signal intensity by doing two different type of experiment. Once with the 90 degree pulse plus y and minus y, take the difference, we could suppress the natural abundance carbon. With the refocused inept, you are able to put a delay, convert antiphase into in phase, so we can do the decoupling. So we did that experiment and we saw there is a gain in the signal intensity. And of course, depending upon the delay what you are going to use in the refocused part of the inept sequence, we can identify different carbons attached to different protons depending upon it is a 1/4J, 1/2J or 3/4 of J. And then we can identify CH, CH2, CH3 carbon based on the phases. In some cases its signal is going to be 0 and other two cases it is going to be positive or negative. Based on that we can identify everything. I saw that polarization, I showed you the polarization transfer is used in depth also, and I just show you one example what we discussed earlier about depth in carbon 13. Depth, it takes the advantage of signal enhancement due to polarization transfer, but still you can utilize it to identify different carbons. There is a subtle difference between APT and depth. Both are used only for identification of different carbons attached to different protons. I hope you got the idea about polarization transfer, depth APT experiment, INEPT experiment, how we can use to identify different carbon. I told you about only proton, carbon, etc., but you can use it for any heteronuclei like nitrogen 15, any other thing you can utilize for polarization transfer. That's what also I said. So with this I am going to stop. From next time onwards we will go to a different topic called two-dimensional NMR. So I will stop here. Thank you very much.